Hey, how's it going? Leetcode 2444. Count subarrays with fixed bounds. You're given an integer array nums and two integers min k and max k. A fixed bound subarray of nums is a subarray that satisfies the following conditions. The minimum value in the subarray is equal to min k. The maximum value in the subarray is equal to max k. Return the number of fixed bound subarrays. A subarray is a contiguous part of the array, and I assume it wants non-empty version. Well, it would have to be non-empty in order for there to be a min and a max. So, okay, this sounds fun. Let's start by, obviously we can't have anything less than min k, and we can't have anything higher than max k. So let's split this up into smaller arrays. So we will say, I don't know, a s. No, that's a reserved keyword. Just a, whatever. Like that. Okay, and then we will say, for I in nums. Yeah. So if I is greater than max k or I is lesser than min k. Now wait a minute. We don't explicitly say that min k is greater than max k? Okay. If min k is greater than max k, then return 0. There, now it's solved. Okay, if I is greater than max k or I is less than min k, then a dot append, boom, like that. Otherwise, a last index dot append I. Yeah. Let's say if a -1, yeah, so if it's non-empty, basically. All right, now we need to see which of these are potentially valid arrays. So a equals ARR for ARR in a if, well, first off, if length of ARR, which I don't think that's going to be a problem, but I just want to make sure, and min of ARR equals min k. I feel like I'm doing Haskell or something. And max of ARR equals max k. Because if it doesn't have the min and max, then we're just sort of wasting our time. So we'll still have to, appease these, but we just want to make sure that it has the pieces in there. And I was thinking of, like, is it in there? I don't know. I think this is fine. And it should be fast enough, and that's what's important, right? Okay, now we need to figure out the... now we have a set of subarrays. Each one of these should be a valid subarray, but the question is, can we, reduce it? So let's see. Yeah, so CNT equals 0 for ARR in A. Okay, so what do we know? We know that this is going to have a min and a max. And okay. I feel like cases where the min and max are the same are going to be unique. Because then we can't separately say, okay, we need a min and we need a max. It's just going to be a little bit weird. So, and that would also allow it to have an array length of 1. So let's see here. Yeah, so if min k equals max k, that's a special case. How many are there? Is it I minus 1? Well, there would be a start and there would be an end, right? Here, I want to see this. For I in range, I don't know, 10 or something. For j in range I, so that's the ending spot, up to 10 plus 1? The end has to be inclusive, right? So it's plus 1. No, I think this is right, because this is valid indices. We just make it inclusive, right? Yeah, and then CNT plus equals 1. Ah, crap, I didn't define CNT. CNT equals 0. Print CNT. Okay, 55. So that is... okay. In that case, n equals length of ARR, and then CNT plus equals n times n plus 1 divided by 2, and return CNT. So in this special case, we can have any combination as long as we select at least one of them. There's nothing in here that says it has to have a minimum length of 2, right? No, it does not. So let's see if this makes sense. So for length 1, you would have 1 times 2 divided by 2 is 1. If you have 2, it would be 2 times 3 is 6 divided by 2 is 3. So the first item, the second item, and then both items together. Okay, yeah, I think that makes sense. Now, it's going to be a little different if we have a separate min and max. We have to make sure that we pick up a min and a max. I think what we should do is I think that we should define it in terms of leftmost min value. Is that going to work? Yeah, I think we need an index of every min value and an index of every max value. This is very similar to a different problem that we did recently. So let's say min values equal, I can't do it that way. Min values and max values, and we'll say for I in range length ARR, then if ARR of I equals what? Equals, well, min value. Then mivs.append I, then same concept. If it equals max value, this is probably a more efficient way to do this. This is probably one of those times I should be using a stack, and it's just so unintuitive to me. Okay. So now we have a list of min values and a list of max values. Now we're going to say for I, which is going to represent the leftmost position of our subarray, in range, let's see, length of error, sure, yeah. And I just realized that if I did it like this, I probably could have left the ones in there, but whatever. This works. Okay, so if, not if, while MIVS and I is greater than MIVS of 0, not greater than or equal to, just greater than, then we're going to say MIVS dot pop 0. And same thing. So this will give us the next min value and the next max value, and they have to be strictly greater than or equal to our current index. Okay, now, if length of MIVS equals 0, or length of MAVS equals 0, then not return, then break. We're done. We have exhausted this array. There are no more combinations available. Otherwise, we're going to have the minimum viable, this is getting ridiculous, just right min, does that even make sense, equals max of MAVS and MAVS. In other words, that's how far right you have to go in order to start at position I and include both a minimum value and a maximum value. So hopefully that makes sense. And then the number of subarrays that start at I would just be that up to the limit. So what is it? It's length of ARR minus 1 minus right min, right? No, not minus 1. Because think about it. If you have to go to the very last position, then right min will be length of ARR minus 1, which means this should give you 1. But if it's the one before that, then there's two different possibilities. You can either start at the very end, or you can start at the next to the end. All right. Hopefully that works, because that's my idea, and that's my only idea. And all right. Let's pray. Because if it's too slow, I don't really know how to speed this up. All right. Beats 5.23%. Well, it's not something to write home about, but let's see. Sliding window intuitive solution. Do we want to figure out something else? Not by looking at C++, I don't. All right, see ya.